Hi everyone, we are first year biomedical engineering student of University of Malaya. Today we would like to explain about our group assignment which is about below knee prosthetic under KIB 1015. I'm Kavita Shri Anapurumpan K. Tanabalan together with Aruni Vijayakumar, Yashwini Raghavendra Tayalan and Arya Omna would like to explain about below knee prosthetic.
Below-knee prosthetics are essential for helping individuals regain their mobility and independence after a lower leg amputation. In this study, we explore the dynamic behavior of these prosthetic limbs using mechanical dynamics and 2D motion analysis. The prosthesis is broken down into three main parts: the socket, pylon, and foot, and analyzed using free body diagrams, orthographic views, and real-world load measurements. We focus on key forces like body weight, ground reaction, torsional stress, and inertial effects, especially during the stance and swing phases of walking. A real-life case study helps us understand how these forces interact with the prosthesis in actual movement. This isn't just about static structure, it's about how motion and force work together in a dynamic system. By combining biomechanics, materials, science, and engineering principles, we show how better dynamic modeling can lead to improved comfort, shock absorption, and overall prosthetic function. Ultimately, our goal is to create smarter, more user-friendly prosthetic designs that move naturally with the body. The objective is to investigate the motion and forces involved in the gait cycle of a below-knee prosthesis, constructing free body diagrams to represent the forces and moments acting on the prosthesis during different phases of movements, determining the axial, bending, and torsional loads experienced by the below-knee prosthesis during walking or running, calculating stress distribution and potential deformation in critical components such as socket, pylon, and foot mechanisms, identifying key parameters, for example, alignment, material stiffness, joint mechanics, which affecting the prosthesis efficiency, and propose design improvements to enhance mobility and reduce energy expenditure for the user, analyzing the kinematics of possible slider or fallbar mechanisms in prosthetic designs and discuss advantages and limitations of the different mechanisms in real-world use, and suggesting another mechanical device, for example, exoskeleton orthotic brace that could benefit from the kinematic or kinetic analysis used for prosthesis.
Now I would like to explain about introduction. Under introduction we will discuss about the structure of below knee prosthetic. So there's a three part of below knee prosthetic which is socket, pylon and foot. Next I'll explain about the methodology. First we went to the Center of Prosthetic and Orthotic Engineering to ask permission and arrange the schedule to take picture of a below knee prosthetic. A briefing and explanation about below knee prosthetic were given by the staff. We identified various types in a below knee prosthetic and took a picture of them. All the structure in below knee prosthetics was measured using measuring tape. All the data had been collected was jotted down. The staff also lent us a manual book of prosthetic to look at the below knee prosthetic measurement. A report was written based on the observation, calculation and the result that were gained. Next, we move to calculation and result. Under calculation and result, we will discuss about three things. First one is free body diagram and orthographic projection. Second one is assumption and specification, which is used for the results. Third is moment of inertia, torque, kinetic energy, axial load, bending moment and bending stress. First, we will look at the free body diagram. There are three forces acting on the below knee prosthetic. The first is normal force, which is acting upwards. Second is weight, which is acting on downwards. There are also force labeled as P, which is a force applied at the prosthetic foot, which is acting upwards. When a below knee prosthetic is in equilibrium, the total force and the total movement is equivalent to 0. Now we move to orthographic projection. First is the front view, second is side view, third is the top view, and the last one is from the bottom view. Now we will look at the assumptions and specifications. First, the prosthetic limb is modeled as a rigid uniform rod for simplicity. Second, the length of the prosthetic from knee to foot is estimated to be 0.45 meter. Third, the mass of the prosthetic limb is taken as 3.5 kg. Fourth, during the swing phase of walking, the angular velocity at the knee joint is assumed to be 2.5 rad per second. Fifth, the angular acceleration is assumed to be 2.5 rad per second square. Sixth is a typical walking speed of 1.2 meter per second is considered. Seventh, the user's body mass is taken as 70 kg, resulting in gravitational force of approximately 686.7 Newton. Last but not least, during heel stick, the ground reaction force is assumed to be peak at 1.2 times body weight as supported by biomechanics literature. Next, we move to the calculation part. First is moment of inertia, where it measures of an object resistant to rotational acceleration about an axis. The formula is I equals to 1/3 ml square. M is the mass of below knee prosthetic and L is the length from knee to foot. So, according to the assumption, M equivalent to 3.5 kg and L equivalent to 0.45 meter. So when we substitute in the formula, we will get I equivalent to 0.236 kg meter square. Next, we move to the torque at knee joint, which is the rotational equivalent of force. The formula is T equals to I alpha. I is the moment of inertia and alpha is the angular acceleration. According to the assumption, angular acceleration is 2.5 rad per second square, and as from the calculation, we got I is equivalent to 0.236 kg meter square. So when we substitute into the formula, we will get T equivalent to 0.59 Newton meter. Next, we move to the kinetic energy during swing phase. Rotational kinetic energy helps to determine how much energy is needed to move the prosthetic limb during walking. So the formula is Ke equivalent to 1/2 I omega square. Omega is angular velocity and we know the I value. I is the moment of inertia. When we substitute into the formula, we will get kinetic energy equivalent to 0.7375 joule. Now we will look at the axial load during stance phase. During the stance phase, the prosthetic must support the body weight of the user, assuming a ground reaction force that reaches 1.2 times the body weight. From the assumption, we assume the user body weight is 70 kg. So, F equivalent to 1.2 times 70 times 9.81. 9.81 because of the gravitational force. So, we will get the total force equivalent to 823.32 Newton. Now we will look at the bending moment at mid-pylon. To estimate the maximum bending moment experienced by the pylon during mid-stance, the axial load is assumed to act at a distance level arm from the pylon's fixed point, which is knee. So M equivalent to Fd. So force we already got from the axial load. So M equivalent to 823.32 times with 0.225. We assume the distance is 0.225. So M equivalent to 185.247 Newton meter. Last but not least, now we will look at the bending stress in the pylon. To calculate the bending stress, we assume the pylon is a hollow cylindrical tube or a solid rod with a radius of 0.015 meter. So from the calculation, we got M equivalent to 185.247 Newton meter and C is assumed by 0.015 meter, which is the outer radius, and I equals to pi over 4 r power of 4. So when we substitute the r, we will got I equivalent to 3.98 times 10 power of negative 8 meter power of 4. So now only we finding the bending stress. The formula is equivalent to mc over I. So when we substitute, we will get the bending stress equivalent to 6.98 times 10 power of 7 Pascal. We can also change it to 69.8 megapascal.
Hello doctor, my name is Arya Yumna, and for our discussion, the result of our analysis helped us understand the dynamic behavior of a baloney prosthetic during walking, which was the main goal of this project. And one of our key objectives was to investigate the motion and forces involved throughout the gait cycle. From our calculations, we could clearly see the difference between the stance and swing phases. This gave us a solid understanding of how forces change during movement and how the prosthesis needs to respond accordingly. During the stance phase, the prosthetic must support the user's body weight, which can go up to 1.2 times the actual body weight, around 824 Newton in our case. In the swing phase, we analyzed the angular velocity and acceleration of the prosthesis and found it requires a torque of 0.89 Newton meter and approximately 0.74 joules of energy to move the leg forward. These values are relatively low, suggesting that a well-designed prosthesis can help the user walk with minimal energy expenditure. To better understand how the prosthesis handles forces, we constructed free body diagrams of the socket, pylon, and foot, which helped visualize the rules of gravity, ground, reaction, and inertia. Another objective we had was to determine the axial, bending, and torsional loads acting on the prosthesis. As mentioned earlier, the axial load was about 824 Newton during the stance phase, and the bending moment at the midpoint of the pylon was calculated to be 185.4 Newton meter. The bending stress in the pylon was found to be 175.8 megapascal, which is far below the yield strength of titanium, which is 800 to 900 megapascal. This reassures us that the prosthetic components are safe and won't fail under regular walking conditions. We also explored the stress distribution and any potential deformation in critical prosthetic components. The stress analysis confirmed that the design and materials used, especially the titanium pylon, are strong enough to handle daily dynamic loading without deformation. This is important for long-term durability and user comfort. We considered alignment, material stiffness, and joint flexibility, which all affect performance and energy efficiency. A misaligned or overly stiff prosthetic can cause fatigue, while proper alignment and flexible lightweight materials like carbon fiber or titanium improve natural movement. Additionally, we looked into joint systems like slider and four-bar mechanisms. Sliders are simpler, but four-bar linkages offer more realistic knee motion, although they are more complex and need fine-tuning. Finally, the same dynamic and mechanical analysis applies to other biomedical devices such as exoskeletons and orthotic braces. These devices also rely on joint motion and force transmission, and using similar kinematic and kinetic principles helps improve their performance and safety. This shows that the insight gained from this prosthetic case study have wider relevance in biomedical engineering. Overall, this project provides a solid understanding of how dynamic analysis guides the design of better, safe, and more comfortable prosthetic limbs, as well as other assistive technologies. That's it from me. Thank you so much.
Limitations: fit and comfort related issues. Challenge: achieving optimal fit and comfort. Socket fit: must match user's anatomy to avoid discomfort and pressure sores. Limb volume changes vary due to age, obesity, or muscular atrophy. Customization: difficult and time consuming to modify sockets for each user. Result: chronic issues with ideal fit, reducing prosthetic effectiveness. Number 2. Limited range of motion. Issue: limited motion in some prosthetic designs. Trade-off: stability and load bearing often reduce mobility. Natural motion: difficult to replicate intricate limb movements. Impact: inhibits freedom of movement and quality of life. Solution: requires innovative designs and materials to enhance motion without losing stability. Improvement 1. Improve socket design. Solution: use of 3D scanning and printing for better personalization. Benefits: enhanced accuracy, reduce discomfort, fewer pressure sores, adaptive materials, adjust to limb dimension changes, improving fit. Outcome: better user experience, longer device lifespan. Number 2. Limited range of motion. Solution: flexible adaptive joint mechanisms for natural movement. Materials: lightweight fiber reinforced polymers and composites. Benefits: increased flexibility, maintained strength and durability. Outcome: greater freedom of movement, improved quality of life.
This dynamic analysis of below-knee prosthetics highlights how motion and forces transmission work together throughout the gait cycle. Using free body diagrams, we examined key components such as the socket, pylon, and foot to evaluate axial bending and torsional loads during both stance and swing phases. High stress zones were found out at the socket pylon and pylon foot connections, pointing to the need for strong materials and smart structural design to ensure safety and comfort. Performance is influenced by alignment, material stiffness, and joint mechanics, all of which affect energy use and user fatigue. We explored improvements like lighter pylons and adaptive foot systems to enhance mobility and also looked at mechanical linkages like fall bar and slider systems for more natural motion through challenges remains. These findings not only guide better prosthetic designs but also apply to devices like exoskeletons and orthotic braces, showing how engineering can truly improve lives. These are some of the references we referred to.
That's all from us. Thank you so much.